so circles part 5, we've got segment relationships. There's basically 2 key ones, and one of them kind of splits into several formats. So the first one is if our segments are inside our circle. I've drawn this as 2 chords. It technically could be pieces of a segment, secant line, but the emphasis is we're only interested in the side lengths inside. And what I want you to think about is we actually know where the relationship is coming from, and that's where I want to highlight real quick, and then we're going to cut to the chase about a little trick we can use to simplify the process. So the key is, this problem actually comes down to similar triangles. And you might be saying, where in the world is this guy getting similar triangles? But hear me out. I'm going to connect a line from A to D. And I'm going to connect a line from B to E. Okay, not perfect because I'm doing that freehand, but we get the basic idea. Here's what I want you to think about. I know some of these angles are the same. Specifically, I know that these 2 must be the same because they're vertical angles, and I don't think anyone would object to that. But there's another detail. Consider angle A. I know that angle A is going to have intercepted arc D to E. Okay. I also know that angle B is going to have intercepted arc D to E. If 2 angles have the same intercepted arc, and they're the same kind of angle, A and B are both inscribed angles, then it must be that they also have the same angle measure and are therefore congruent. So now I've got 2 triangles that have 2 angles the same, which means they must be similar triangles by angle-angle similarity. Now, if I match corresponding parts, I can set up my proportions and I can figure it out, and that's always an option for you. But we can also cut to the chase, because we know the moment we set up our proportions, we're going to cross multiply and start simplifying. Well, it turns out that when you do that, you end up with the following. If you have chords that intersect and you've got segments inside, then I want you to think about this. Piece by piece. Okay? That means the following. If I look at this picture, DC is the first piece. Times that by CB, and that'll be the same for the other piece. A to C times C to E. Piece by piece. So for example, if I threw some numbers on here, say I said DC was 5 and CB was 10. I don't want 10. Let's go 8. And AC was 2 and CE was X. Well, if we plug all of that in, DC is 5 times CB is 8, AC is 2, CE I don't know yet, I'm going to call it X. So I would get 40 is equal to 2X, or X must be 20. Okay? And so we can work it out in that way, piece by piece, because of those similar triangles. Now, a lot of times these problems will have x's involved. You might have to use some factoring quadratic formula to get your answers. But that in essence is the core of that problem. Now this rule changes a little bit when I move the pieces outside. So suppose this is now my image, and these are the segments I'm talking about. I've got 2 secants now. Well, it's still similar triangles. And what I want you to think about is this picture is very similar to one that we saw a ton in chapter 4. Do you recall way back when we had, ignore that smudge right there, you've got a tree, you've got a person standing in the shadow so that their shadow matches up with the tree's shadow, and we had those similar triangles, and the whole point is they were both right angles. And when we did this, we took the small piece times the leg of the big triangle, and then we took the hypotenuse of the small triangle and the leg of the big triangle. We kind of had that sort of similar triangle relationship. Well, guess what? This is the same picture structurally. It looks different, but at its core it's the same. And the key is you've got a small triangle and a big triangle, and they share this angle in common. Well, guess what? I got a small triangle and I got a big triangle, and they share angle A in common. So what does it come down to? If I've got segments outside, instead of being piece by piece like it was above, my relationship is now outside times whole. That is to say, small triangle times the big triangle. Okay? So, in this case, if I were to set it up, I would have outside AB times the whole AC must be equal to outside AD times the whole A all the way to E. Okay, so outside times whole equals outside times whole. Now let me think of a few numbers so we can do a demo for this. I'm going to say that, let's just keep this simple. Let's make this, let's do 5 and 10 again. That worked out pretty well. 5 and 10, and then we'll make this X, and this, we'll just make it 12, why not? Okay, so if we plug that in, AB is 5, AC, let's be careful, A to C, 5 plus 10 gives me 15, AD is X, and AE, A to E, is going to be X plus 12. Ooh, gotta be careful. Okay, 5 times 15 is 75. Distributing by X, I get X squared plus 12X. Well, if I'm going to do this properly, I need to move the 75 over to the other side. So I've got 0 is equal to X squared plus 12X minus 75. And now you've got a choice. I'm pretty sure this isn't factorable because I've got 3 and 25 and 5 and 15, and that's about it. So I can't factor. So I've either got to complete the square or use quadratic formula. I'm going to go ahead and highlight using quadratic formula because that is a skill you need for this test, but you may use completing the square and that is valid. So I'm going to come over here and I've got X squared plus 12X minus 75. So I'm going to go to a new piece of paper, and I know that quadratic formula is opposite of b plus or minus square root b squared minus 4ac all over 2a. So if I start plugging in, opposite of b is negative 12 plus or minus the square root. B squared, 12 squared is 144 minus 4. A is 1, C is a negative 75, all over 2 times 1. Okay, so I've got negative 12 plus or minus the square root, 144. I'm going to have minus a negative, so that becomes plus. 4 times 75 would be 150 doubled, so plus 300. all over 2. So then from there I've got negative 12 plus or minus the square root of 444. That's kind of fun. All over 2. And let's see, if I want to break down that 444, I know I can take a 4 and a 111, and the 4 breaks into 2s. And I want to guess a 111 should have a 3 in it. So if I take a 3 out, that would be 30, 111. I can't think. Divide by 3. 3 would be 9, that'd be 21, so that'd be a 37, right? 90, 21, and 37. Okay? However, 3 and 37 don't have pairs, so that means that that's equal to 2 root 37. Oops, sorry. Root 111, because there was no pair to come out. So that means if I come over here, I get negative 12 plus or minus 2. Buddy breaks out of jail. Root 111 all over 2. And then remember, if I'm going to simplify this properly, I can't just cancel and 1, just the 12 and the 2. I have to essentially look for the triangle because I need to make sure it comes out of each piece of the addition step. So my final answer is going to be negative 6 plus or minus root 111. However, because I'm talking about arc length, it does not make sense to have a negative measure for segment length, not arc length, my apologies, which means I can just keep one value, negative 6 plus root 111. And that would be the answer for that x value right there.